Okay, this video clip continues from the first one as we give you an introduction of the subspace identification method. The method involves two main steps. The first main step is to remove the effect from input and effect from noise from the data equation. This step involves using orthogonal projection. And the second step is about performing SVD factorization on the system on the matrix G. So in this short video clip, I would like to review about geometric tools that involve orthogonal projection and also RQ factorization. Okay, first of all, RQ factorization has a very close relation with the QR factorization, but I just so I'm going to explain here what we're going to use in the subspace method. So suppose you have a matrix A that is in this case I consider the fat matrix, because the fat matrix is what we're going to see in this in our context of subspace ident. You have a matrix A with size of n by m. An RQ factorization will give you a factor R and Q where the matrix R is lower triangular with a size of n by n, and with the factor Q that has size n times m. Okay. These, okay, the full RQ factorization is given by the right hand side. So is a matrix R that can be partitioned into R1 and 0. Okay, this is called full RQ. All right, and the matrix Q, if you partition in the row, all right, it is going to have the block row Q1, the block row of Q2. The size is the following. The rows of Q1 is n, the rows of Q2 is m minus n. Okay, so the full RQ is the result is going to be, it end up with the same this RQ when Q here is fat, because if you multiply these two guys together, you get that it is going to be R1 Q1 plus 0 times Q2, and it's enough with R1 Q1. So our R1 Q1, so our R is basically R1, our Q here is Q1. Okay. In the full RQ factorization, we say that our Q is given that Q has orthogonal rows. So that means when you multiply Q with the Q transpose, which is Q1 and Q2 transpose here, you're going to have Q1 transpose, Q1 Q2 transpose, Q2 Q1 transpose. This guy has to be identity matrix by the assumption of this RQ factorization. It has orthogonal rows, so this part will be identity matrix. This part will be 0. The rows are orthogonal. Orthogonal is related to orthogonal. So each row are orthogonal, but each row is normalized such a way that its norm is 1, and that is called orthogonal. All right, the matrix R, as I said, is lower triangular with the non-negative diagonals. It's non-negative, which means it could be 0. Some of them could be 0, some of them can be positive. If the rank of A is n, if the rank A is what we're going to see here is A is generally fat. If rank of A is n, or A is full row rank, we can show that the diagonals of R are all positive. not only non-negative but positive. Okay, and it has a factorization as I illustrate in this picture. Okay, full RQ will give you a factor R and Q. Okay. That's RQ factorization. I will explain shortly how RQ factorization is related to the problem we consider here. And here I would like to explain about orthogonal projection. We see orthogonal projection before when we mentioned about the least square estimation, right? Remember the concept of least square? So a problem of a least square, okay, when you get beta hat from the least square, you multiply it with x. That is your y hat, okay? The problem of finding the least square estimate is the same as finding the projection of y onto the range of x. The range of x is also the same as column space of x, right? So here, orthogonal projection we see in this slide is very closely related to that concept, but we change the concept from column space to the row space instead. In this setting, we have a matrix U that has size of R by N. Our big N is going to be is going to have the meaning of, you know, the number of samples in your data. Okay, typically your U is going to be a fat matrix, which means N is huge compared to the rows of U. Okay, so the row space of U, what is the row space? The row space is okay. Let me recall. City Park, what is the row space?
Row space is the row of matrix U that made the basis of.
So yes, the row space is a collection of linear combinations of row vectors in U. Okay, so if you have a matrix H that multiply with U, okay, and in this way you write H as H1, H2, HR, okay, this is your H, and you multiply it with U, that you write it so that it contains R rows, all right, and that's going to be H1 U1 transpose HR UR transpose. This vector, I call it V. This V, we say that this V is in the row space of U because it is a linear combination of rows in U. You get a matrix in the row space of U when you multiply a matrix, some matrix H on the left hand side of U. This is something different from what we learned in the least square. Remember, this y hat, when you multiply beta with x, this y hat, if you partition x into n columns, your beta has n elements, right? You multiply beta on the right hand side, and then you see that it is the results of this multiplication says that your y hat is a linear combination of columns in X. So y hat is in the column space of X, or what we call the range space of X. Okay, see the comparison of these two approaches. If you want to express a vector or a matrix or anything that is in the row space, you multiply a matrix on the left hand side. If you represent anything as a vector in the column space of X, you multiply something on the right hand side. Okay, that's the concept of row space. Okay, Next, next we define pi as the orthogonal projection in this way. It's not actually that what we define. Actually, it can be shown. It can be shown that when you specify pi this way, U transpose U, U transpose inverse U, that is going to be orthogonal projection onto the row space of U. Which means if you multiply pi on the right-hand side of any matrix M, the result M pi here is going to be the closest. So you have M, so you multiply M with pi on the right-hand side. This guy is going to be the metric that is closest to M in Frobenius norm sense. And this metric is in the row space of U. Okay, so it's different subspace we consider here. Okay, here we can prove it. We can prove it that it's an orthogonal projection. We can prove that M pi is the closest matrix to M, but I'm gonna leave that proof for now. Just stating the result. So the residue after the projection, if you okay, subtract M pi, right, the projection from the original matrix M, that is what? That is this portion. That is the residue. Okay, you can see that you can factorize M. This matrix here, I minus pi, we're going to label it as pi perp with the symbol perp to mention that this is also another orthogonal projection, but it projects onto the orthogonal complement of row U. Let me recall that when you have a subspace M, okay, we can also define orthogonal complement of M using the symbol perp. M is a subspace, all right. M perp is a collection of Y, so that the inner product between Y and X is always 0 for any X in M. Basically, M perp, if a set, we can also show that is a vector space. It's a vector space that contains all the vectors that is orthogonal to everything, to all the members in M. That's why they call it orthogonal complement and use the notation M perp. Okay, here we say that there is also another matrix use the notation pi perp, and we define it in such a way that it's I minus pi. This one is also another orthogonal projection matrix, but instead of mapping M to the rows of U, it maps M to the row of U perp. Okay, and with this, okay, and we have the relation. We have this simple fact from linear algebra that row of U is a subspace. All right, orthogonal complement of row U is going to be, first of all, we have the fact that the row of U is actually, the row space of U is actually the column space of U transpose. This can be proved. This is from linear algebra. Column space, which is the same as range space. Okay? You can use this notation. And the next step is range space of U transpose perp is the same as range space of U. Which means if you have range of A perp, that is the same as range of A transpose. That is a fact. Okay. So basically what I'm trying to say here is that orthogonal complement of the row space of U is actually the column space of U. Okay. As we mentioned previously, pi perp is orthogonal projection to row U perp, to row space of U perp, but we just show that row U perp is the range of U. Okay, which means your pi perp is orthogonal projection that projects to the range space of U. Okay, and that shows that when you multiply U with pi perp, that gives you 0. Okay, that gives you 0. That result, if you want to, hold on. If you want to show it from the expression of pi perp instead, is okay too. Okay. So let's see here. U times pi perp. U times pi perp. Okay. If I multiply U on the left hand side, I will get U which is, so if you multiply it, it's going to be U minus U transpose, right? U transpose inverse U. And that is U transpose times with its inverse. That's going to be identity matrix, right? So you get U minus U, which is 0. This is going to be a very important equations, all right? Because you're going to use pi perp orthogonal projection into the that is orthogonal projection onto the range space of U or the row of U perp. It means that you multiply U, it gives 0, and from our data equation, wherever we have the terms U, so if you multiply with U perp, that term disappears to 0. We will use it. Okay. Next, I would like to explain briefly about, okay, let me go back a little bit. I use this pi. I also mentioned the subscript U to make a note that this pi is associated with the matrix U. Okay, you can define pi with another matrix as well, like M. Okay, so basically the description of pi depends on U. All right, if you use U, this pi give orthogonal projection on the row space of U. Okay. Next, now we're gonna combine the two concepts of both RQ factorization and orthogonal projection to explain connection with the results from the least square. But this is going to be the least squares on the matrix variable. Okay. I would like you to compare the concept of least square we learned previously. This is about, again, finding projection of y onto the range of x or the column space of x. And you see that the rows of beta, it multiply with x on the right hand side. Now in this slide, we consider a least square problem in the matrix form. The row of our x, which is a sensor matrix, the analogy here is a matrix H. So H plays the rows of x. Our beta is actually theta. Theta plays the role of unknown parameter that's going to be estimate. But you see here that theta multiply H on the left hand side instead of the least square we see before, beta times x on the right hand side. Okay, here the problem is y and h are given. All right, these are matrices. Y is going to be your measurements. H is going to contain both y and u. Okay. Apart, if you look at multivariate, vector AR equation, you will end up with this formulation. So the least square solution can be derived using the zero gradient and everything, and it turns out that the solution is given by this. I would like you to compare with our state space, our previous least square. So your beta hat is going to be X transpose X inverse X transpose Y. Okay, the role of pseudo inverse here is different. Okay, X transpose inverse is a left inverse. Okay, and this is going to be something else. Okay, left inverse. So this is going to be the right inverse of H, because if it's multiply this guy on the right hand side, it gives you identity matrix. So there's always some analogy between, you know, the least square we see before and the least square in this slide. Okay, so I would like to mention that, okay, this is the problem of projecting y onto the row space of H, because theta is left multiplied to H. So when we solve this least square, we will use RQ factorization, just like the same way we explained in the least square lecture, that we're going to use QR factorization in our least square form. So this is a least square in the matrix form. We use RQ. Okay, so suppose that you get the RQ factor. This is your R, this is your Q, all right? This Q has orthonormal rows. When you expand everything out, H is going to be R11, Q1. Your Y is going to be this matrix, you know, the RQ factors. Okay, now if you associate with the concept that, okay, your Y is going to be a projection, sorry, your Y hat, which is theta hat times H, okay, that Y hat is going to be a projection of Y to the row space of H. So here we define the orthogonal projection associated with the matrix H, and you get pi perp here. We can verify that the theta least square, your estimate, which is given by this, it actually can be obtained in the RQ factor like this. Okay, so I'm going to show you a little bit about this, maybe just one result. Okay, first of all, okay, let's see. So I'm going to show this expression that the least square estimate, you know, so theoretically it's given by this expression. I'm going to show that it can be also obtained from the RQ factors. So first of all, let me calculate H transpose. Okay, H transpose is R11 Q1, right? And Q1 transpose, R11 transpose. But because my Q has orthonormal rows, right? So my Q1 transpose is
an identity matrix.
Right, so it gives me R11 transpose. Okay, and next I'm going to calculate YH transpose. YH transpose is going to be R21 Q1 plus R22 Q2. Okay, I put it here. And my H transpose is going to be Q1 transpose R11 transpose. Now I'm going to multiply everything out, but when I see these terms, when they are multiplied to each other, I know that, okay, first term, I'm going to have R21, all right, and R11 transpose. Okay, everyone see this? Because Q1 transpose is identity matrix. All right. The second term, I'm going to use the fact that Q2 and Q1 transpose is ping. What is it?
It's 0.
Is 0. Okay. So so it's 0. Okay. So now after that I get theta hat LS is going to be 1 1 transpose with this guy inverse, right? And that gives me 1 and what is it? 1 1 inverse, right? And that is given by this expression. So this is how you actually compute the least square estimate numerically, perform RQ factorization, and every quantity that involves in the least square estimation can be obtained by the LQ factors. I also have the expression, you can verify it in the same way. Theta times h, that is the meaning, has the meaning of your y hat. That is orthogonal projection of y on the row space of H. So that's given by y times pi, all right? And if you just work it out with this expression, as I explained previously, that is obtained by R2Q factor and Q1. Okay, so it's this and this. And y minus theta hat times H, that is the residual error after the projection, okay? You project y, all right, you project y onto the row space of H. Of course, the optimal residual will belong to the row space of H perp, and that's given by y times pi perp, and you can show that it's given by the RQ factors. So that's a short introduction about the tools here. You see that all the tools here just play with the matrix factorization, orthogonal projection. That's the concept from linear algebra. Okay. All right. In the next video clip, we will see how you're going to use orthogonal projection to remove the effect from noise and from the the effect from noise and the effect from the input from the data equation.